In previous classes we have discussed the case of a particle trapped inside a box and also the case of a harmonic oscillator. We saw that confinement in general leads to extreme energy quantization and restrictions of particle movements. Today we are going to discuss another problem in which we consider the case of an electron at a potential barrier. So let's consider a beam of particles of mass m approaching a square potential barrier defined by these expressions. So the potential is 0 up to this x is equal to 0 reference level, and it has a potential of V0 for the range of x from 0 to a, and then again after a the potential drops to 0. So we basically have a beam of particles coming from the left side, that is in the region 1 marked here, and then it encounters a potential barrier on its path when it tries to go to this region 3. Here a is the width of the potential barrier and V0 is the height of the potential barrier. Classically, if the energy of the particle is less than this barrier height, it will always be reflected back at this barrier, and if E is greater than the barrier height, it will be transmitted to region 3. So let's analyze the problem quantum mechanically. So first let's see what happens if the energy of the incident particles are less than the barrier height. Now the time independent Schrodinger equation is given by this one, and we are familiar with this expression. We have used it many times so far. Now we are going to write or rewrite this time independent Schrodinger equation for these three regions marked here, region 1, 2 and 3. So for the first region, it can be written as d square psi 1 by dx square plus 2m e by h cross square psi 1 equal to 0, because the potential is 0 in this region, so there is no potential energy term appearing here. If we substitute 2m e by h cross square as some constant k square, we can write this equation as d square psi 1 by dx square plus k square psi 1 equal to 0. In region 2, we modify the Schrodinger equation like this one, as the potential energy in this term is V0, which we assume larger than the energy of the incoming particles. So we rearrange these terms, positions of potential and kinetic energy, and then we put negative sign here. Again we make the substitution for this quantity 2m V0 minus e by h cross square by some another positive constant alpha square. Then we can write this Schrodinger equation as d square psi 2 by dx square minus alpha square psi 2 equal to 0. In region 3, again there is no potential in that region, and hence the Schrodinger equation looks similar to that in region 1, that is d square psi 3 by dx square plus k square psi 3 equal to 0. Now we have three second order ordinary differential equations to solve, which you know how to do. The solutions to these three equations are given by, for the first equation, it gives the solution for psi 1 as some constant a1 e raised to ikx plus a2 e raised to minus ikx, and for the second equation we get the solution for psi 2 as some constant b e raised to alpha x plus c e raised to minus alpha x, and for the third one the solution for psi 3 is given by d e raised to ikx plus e raised to minus ikx. So all these are constants. A, B, C, D and E are constants appearing here, and this E should not be confused with the energy E here. Anyway, we will get rid of this E soon. The e raised to ikx here represents a plane wave traveling from left to the right, that is along the positive x direction, and e raised to minus ikx represents a plane wave traveling in the negative x direction. So that is this one is the reflected wave. E raised to minus ikx is the reflected wave. For simplicity, let's assume that the amplitude of the incident wave is 1. That means we can take this constant a1 as 1, and then we can rewrite this a2 as simply a. In region 2, we have exponentially growing and decaying waves as the solution, and in region 3, there is nothing on the right side which causes the wave to get reflected back. So we expect a wave traveling in positive x direction only, and hence this constant E must be 0. So these three equations becomes like this with these modifications, where we have considered an unit amplitude for the incident wave, and we don't have any reflected wave in region 3 as there is nothing to reflect this. Now the probability density of incident wave is 1, and that of the reflected wave is the square modulus of A, and the probability density of the transmitted wave is given by the square modulus of D. So the transmission coefficient is given by the modulus square of D, as it is the ratio of the transmitted to the incident current density. Similarly, the reflection coefficient is given by modulus A square. These are connected by the relation R plus T equal to 1, the incident intensity. To evaluate the required constants, we apply the boundary conditions. The boundary condition at x is equal to 0 at this point demands that psi 1 at x is equal to 0 and psi 2 at x is equal to 0 must be same, because both these psi 1 and psi 2 at this particular point represents the same wave function. So the continuity of the wave function at the first boundary demands this condition. That means if you equate these two things, equation 4 and 5, we get an expression 1 plus A equal to B plus C. Similarly, the continuity of derivatives at the first boundary demands that d psi 1 by dx at x is equal to 0 must be same as d psi 2 by dx at x is equal to 0, which gives this expression. If you differentiate these two equations and when you equate it, we get ik minus ika equal to alpha b minus alpha c. There is one more boundary at x is equal to a, which gives us two more equations like this. That is the psi 2, sorry, I made a mistake here. This is psi 2. The psi 2 at x is equal to a must be equal to psi 3 at x is equal to a. So if you equate these two things, putting x is equal to a, this is what we get. And if you equate the differential, here it is correct, the differential of psi 2 and psi 3 at x is equal to a, we get the fourth equation like this. Now solving equation 9 and 10 gives us the expressions for the constants B and C in terms of the constants D, like this. And solving equations 7 and 8 and then substituting for B from equation 11 leads to an expression for A in terms of D, like this one. Upon substitution of these values for A, B and C in equation 7 and further simplification leads to an expression for the constant D as this one. Hence the transmission coefficient is given by this particular expression, because transmission coefficient is the modulus square of all these things. If the barrier is very broad and high, then alpha A becomes a quantity much larger than 1, and hence the sin h and cos h terms appearing in this expression can be approximated as half e raised to alpha A. Then the transmission coefficient can be modified as this if you make the substitution. Now if you substitute for k square and alpha square in terms of energies, it becomes a simplified form like this. Since none of these values are 0, you can see that there is a finite probability for the particle to penetrate through the potential barrier even if its energy is less than the barrier height. This is in contrast to the classical physics, which says there is no possibility for the particle to appear in region 3 if its energy is less than the barrier height. Now the wave functions in 3 regions can be plotted like this. We have seen that there is oscillatory solutions in region 1 and region 3, whereas in region 2 the solution was an exponential function. So the wave function will looks like this. Now if we consider the case of particles having energy greater than the barrier height, there is nothing interesting here. The particle can easily go to region 3. In this case, the only difference is in region 2, where the Schrodinger equation becomes like this. Previously it was written as V0 minus E, but now since the energy is higher than the barrier height, we have rewritten it as 2m E minus V0, and we put positive sign here instead of negative sign. If you put these values as beta square, we can get an equation like this one: d square psi 2 by dx square plus beta square psi 2 equal to 0. So we have oscillatory solutions in region 2 also. Previously we had seen that oscillatory solutions in region 1 and 3, and now we have the oscillatory solutions in region 2 also. So in all 3 regions the wave functions are oscillatory in nature. Hence if you plot the wave functions in 3 regions, we have wave functions like this. Unlike the previous case, here we have oscillatory solutions for all 3 regions. Now if you calculate the de Broglie wavelength in these 3 regions, we can see that the wavelength in region 1 and 3 are same, while the wavelength in region 2 will be larger than these values, wavelength in region 1 or 3, because here the kinetic energy of the particle is less than that in region 1 or 3. So here you have much larger wavelength compared to the wavelength in region 1 and 3.